Cool, cool. Let me check my live stream. It's been a while, so I need to remind myself how to do this. Right. I can hear myself. Perfect. I'm just checking. Yes, I can. I was just making sure my mic is working. It is. Cool. Welcome back, everyone. It's been a while since I've live streamed. Exactly 5 weeks. I think a little more than 5 weeks, and that's because I was learning about LLMs. I was on a LLM vacation. I was trying to learn and understand how to build these systems and also their applications. I've been posting about it, and I was trying to like understand it. First of all, gain the confidence before sharing it. Now that I've done it, although I'm like not there where I want to be, I'm still learning about it. But it's a little better than how it used to be. I'll be kicking off the video series and the live streams again. Yes, Sumit, it's been a long time. That's what I was saying. But the plan is to talk about LLMs, and let me just show you real quick. So usually I have my background clear, but this is the amount of papers I've gone through in the last few days, and that is what I have been up to. I feel like justifying why I've been away to everyone, so that's what I'm trying to do right now. Anyways, today we're learning about Drag Your GAN paper. We'll be going through it and trying to understand it. And this was really popular, I believe. AK, and shout out to AK. I think AK is all we need to stay on top of papers. I always just check my feed and look at any papers AK has shared, and for the most bit that gets me sorted. So I think there we go. AK tweeted about it, and as you can see, it got 3 million views in a day. Not that that's a metric to measure research, but that's a good proxy to knowing that this was a popular paper. So this got me curious. I actually picked up the paper. I saw it as soon as he tweeted it. Basically, every day I wake up, I see his tweets and pick the best paper I like. That's how you see those two stacks there. So this picked my interest, and that led me to the paper. That's why we're reading this. So here's the demo that got really popular. And let me talk through what's happening here. So this is somewhat possible through ControlNet, and that is one of my criticisms of this model as well. That hey, they don't compare themselves against ControlNet. Maybe they finished this work before ControlNet came out, because they do mention diffusion based models. Maybe maybe ControlNet is somewhat similar, but I think with using ControlNet you could get similar results. Regardless, their demo just uses GANs, and this is running on a single GPU, a single 3090, which in today's standard is also an achievement. So what's going on here is you can see that you're clicking on different areas. Sometimes you're defining a mask, so you can define a region of interest, and around that you can manipulate these images, right? So you can move around and you basically drag around things from the red to blue point, and then the GAN sort of fills in this space. So if you're familiar with the latent walkthrough videos that were popular a while ago, it's somewhat similar to that. But the innovation lies in the fact that they're building on top of style GANs, and this is one of the first GAN-based models to be able to like achieve this result where you can actually click and edit through an image, and then the discriminator sort of generates the image we'd expect. So in any child ice stream fashion, what I'd like to do now is I'll give a summary of the paper. So we'll take a look at the summary. If all you care about the gist, if all you care about is the gist, then this should get you started. So the first 5 minutes will give you the gist of the paper, and then we'll really dive into the paper. I'll actually point out the exact details, and we'll go through it bit by bit. That's how I do it, and so far it's worked okay. So I'm just sticking to it. Here are the background concepts we need to know to really understand this paper. So the first one is latent spaces. The second one is StyleGAN v2. So this paper builds on top of StyleGAN v2, motion tracking, and feature maps. So I'll first of all explain these. Here's a refresher of how GANs work, right? And latent space is this space that sort of the GAN builds as it tries to generate images through noise. So inside a GAN, what's going on is you have this random input or random noise that the generator takes in, and there's this real image that the generator competes against. The discriminator sort of identifies which is the real, which is the fake one, and they both improve from each other. So the GAN sort of works with the latent space. You can go into a lot more mathematical definition, but for my purposes, I found that to be like an okay understanding. At least that's how I remember it. Then I wanted to do a recap of StyleGAN V2 paper. And actually, if you go to papers with code, they point out some other facts about it. So let's read through this. StyleGAN 2 builds on top of StyleGAN with some improvements. First, it has a different normalization fashion, which is designed to replace the older one. And secondly, there's an improved technique. This is somewhat relevant. It uses progressive growing, which means as the model trains, you start with a smaller resolution image, and as the model trains, you progressively increase its resolution. So that's how these models work, or that's the innovation bit according to papers with code. Here are some other interesting factors which are relevant to the paper we're looking at. So there's a mapping network inside StyleGAN V2, and please note that this is not unique to it, but the implementation was slightly different. So what does this do? It maps an intermediate latent space. So normally you have your input which directly gets taken in by the generator and get an output from that. Here you have the input which goes to a like middle hidden state, and from there you generate the final output. Generate, sorry. And this is disentangled, which is a researchy way of saying not connected to the input. There are three other factors. These aren't as relevant, but just for the sake of covering StyleGAN V2, I'll mention this noise injection, which happens at every layer, and how they implement learning rate is different. So they have an equalized learning rate for all layers across the model instead of having that fixed learning rate scheduler that we normally use, right? So now the paper, again, we'll come back to this, but Drag GAN builds on top of StyleGAN. So they haven't changed the GAN architecture or the base architecture at all. They've just added some implementations on top of it, which are motion tracking. Oops, I think I didn't copy this properly, so I'll just open up any motion tracking example, or I can just talk through it. So whenever you are doing motion tracking, you're basically tracking how the objects change between frames. So if you were to draw a motion tracking map across these, there are different algorithms, and in the paper they mentioned that traditional CV were the ones that were really popular, and recently deep learning took over. But as I was moving my hands, you'd see dots connecting consecutive frames. So if you've ever seen optical flow maps, those would be somewhat similar to that. But basically, it tells you the difference between successive frames. That's my understanding of it. And finally, feature maps. So these are all the jargons that you need to know to really understand the paper. So I'm just like setting it all up for you. If you remember CNNs, and this is from the famous Zeiler and Fergus paper, which I bring up in every other live stream. But CNN sort of take an input image and then start learning these hierarchical features over and over, and they get more and more abstract with every layer. So these representations are feature maps. How is this connected to GANs? Inside the GAN, there are convolutions that happen at different layers, and this sort of connects to that. So the implementation inside the paper sort of connects to the feature maps, and we'll take a look at it once we get to the paper. So what is unique in this paper, and why was it really popular? My understanding is this demo is somewhat possible in ControlNet as well. That's what I believe. I'm yet to try it. I think I'll give it a try and again post about it. But what is unique is this is totally based on GANs, and it's also running on a single 3090, which is also possible for ControlNet as I understand it. But I'm yet to try it, so I won't make a comment on that. The second thing is it allows multi-point tracking and it allows precise handling. So historically, there was another paper that allowed single points to be traced across images. But as you can see in this car demo, you're moving 2 points across, and that's basically resizing the entire car in that example. And it's the first to allow you to make edits on top of a style GAN. So this sort of feature of being able to use to be able to edit images on top of GANs has existed. There was edit GAN earlier, and this mentioned in the paper, but edit GANs used to build on top of um, segmentation maps. But this paper is the first one that makes it work with style GANs. And the two innovations lie in the implementation of motion supervision and point tracking. So again, this is the gist. We'll get to all of the details, but in one word summaries, motion supervision checks feature maps. So it checks these representations, right? And makes the model generate the manipulated image output. So why did I mention this? This is like very obvious. How they implement the loss, normally you back propagate through the entire equation, right? But from what I understand, they've set up the loss function where they do not back propagate to the original point. So remember, we were moving these images around, and if you were like trying to learn on these points, you'd define a loss function back propagate through that. Inside the paper, they mentioned they do not back propagate the loss through the initial click, only towards the final click. So that sort of, as I understand, helps the model generate the final output. Then the second point is it allows tracking of multiple points, and both of these again are implemented on top of StyleGAN V2. Cool. I think that's all I had for the summary. So now we can jump into reading the paper. And like always, I'll point out interesting sections from the paper, and we can go from there. Before that, real quick mention. I showed all of these papers to you guys, and there's been a request of creating a roadmap for all of you to learn. So I'll be open sourcing that really soon. But in the meantime, I invite you all to join the Discord that will be the place for this. So right under the like button, you can find the link to it. And you can also find other videos I made around GAN. So if you're at all curious, please check those out. But I would say please consider joining the Discord because that's where the discussions and all the interesting things will happen. It's the first link under the like button. Cool. So the paper is titled Drag Your GAN, and now we're actually going through all of the details. So the summary is over, and now we'll read the paper from start to finish. So the paper is titled Drag Your GAN Interactive Point Based Manipulation on Generative Image Manifold. And this, as I understand, the manifold bit sort of refers to the latent spaces and uh, things around that. I'm just like, I've read so many papers and I'm thinking they could have called it editing images or Photoshop is dead, right? Like we criticize a lot of those like tweets that go viral and like have these like catchy titles or somewhat clickbaity. Why not use those for a paper, right? I mean, I'm just curious if there's like a solid reason for it or like if anyone does at all. I would have done it, and probably that's why I'm not a researcher. Anyways, let's get to it. So I've already highlighted the sections, and like always, I've read this paper 4 times already today. So these are just my notes that I've like sort of uploaded to OneNote as well now. So they say they're studying a much less explored way of controlling GANs, which is to drag any point of the image to precisely, which is another key point here, right? Like others have sort of done this, but here the image sort of really sticks around to the point that you care about to reach the target. And this is done through two steps. The first one again is feature based motion supervision, which sort of takes the initial point to the final point. And then they've created this new point tracking which leverages the discriminative generator inside StyleGAN v2. So here again they've shown how this model works. I think the demo video we played earlier gives a better overview. So they talk about what should you care about inside controllable image synthesis systems, and they make 3 points. So the first one is flexibility, the second one is precision, and the third one is generality. uh, this paper sort of somewhat succeeds at the third one, in the sense if you play the video on the website, it sort of comes through when you're editing the horse, right? And this happens when you're working with out of distribution images. Sometimes the model hallucinates, or if the image is occluded, so let's say your teeth are hidden behind the mic like so, it would hallucinate or sort of create disfigured outputs there. And this is a issue with the implementation, and I think it's an issue with control net as well. So it's an issue with all generative models in that sense. In the next paragraph, they talk about why the old approaches fail, and that is because they fail to generalize to new object categories and often control a limited range of attributes and don't provide much control over the editing process. Then they talk about diffusion model, but they make the claim that they're not very they only work through text, so it's text to image. My argument again, I wish they had looked at control net, because I looked at the recent developments in control net, and I think it's like it's really possible to do the same thing in diffusion, which is much more powerful. So later they talk about what's the closest approach to them, and it's called user controllable LT. This also studies something similar, but their approach sort of differs in two different ways, which is that they allow controlling of more than one point, and they handle these like control points exactly. So they handle them more precisely, or the image sort of lands where you would expect it. Um, I think diffusion models also sort of struggle with precision unless you're using PoseNet. So let's say you like apply a PoseNet to my pose that I'm holding right now, and you generate an image. So that only in that case they sort of stick around to it. But I would be curious to see how does that compare. Then they talk about the implementation, and they say it takes only a few seconds on a single 3090, and this sort of makes it a live demo. They have created a GitHub repo which got 4K stars, and they will open source 4K stars in one day, and they will open source their implementation in June. So I don't know when in June, but I'm really looking forward to it. I'm sure everyone else is. That's why it's been so popular. So now they talk about some relevant work, and the main claim is there have existed some form of GANs or some conditional GANs that are similar, allow other things that are somewhat parallel to this, but none have been built on top of style GANs. So that is where the main innovation of this paper sort of lies in. They talk about all different models and how they behave, different things around that. I think we can skip past this. They also talk about how these models that allow motion tracking have existed and which are the most popular ones. They've shared the name to them, and they've pointed out how these work. So they estimate the optical flow, as I had pointed out earlier. If you don't know these terms, the way I have remembered it in my head is they track changes between two frames and sort of create a direction between them. So like let's say if my hand is only moving, it would draw arrows towards the right. between successive frames. So optical flow sort of tracks that across frames. That's the only understanding I have, and I wouldn't personally look at the older papers. So that's why I didn't highlight it earlier. But this is all you need to know. So in this work, they show that point tracking on GAN generated images can be performed, and they reveal that the feature spaces of GANs are good enough for such tracking to be used. So they don't add any new layers, they don't make any changes in the architecture, they just add these like two new features that let them track these features, but they don't make any changes to the underlying architecture. They say they are the first to connect the point based editing to GAN features and design a concrete method which allows interactive editing. So now they talk about their method, and let me just catch up with the chart. Vadim is also here. Great to see you, Vadim. I think Vadim never misses any video of mine. I haven't looked at the Kaggle world, Vadim, but I'd be curious to see what's going on there. I need to log in. I haven't logged into Kaggle over a month now, for over a month. Cool. So let's understand their methodology. Methodology. That's I got it right this time. I'm just looking at my notes. So they talk about a few things here. So they define the terminology. I'm again skipping past this because I'll again point this out. And then they defined how's interactive manipulation happening, and they basically tell you what points are, how we denote them, so on and so forth. So they familiarize ourselves with all of the terminology. They mention latent code is W dash, new image is I dash. I'm skipping past all of this. So let's take a look at the crux of it all. This is the main main secret behind it. So in this work, they propose a motion supervision loss that does not rely on any additional neural network works. And this is what I've been pointing out earlier, that it's only the loss function that they've sort of defined. It doesn't make any architectural changes. The key idea is that the intermediate features that the generator learns are good enough to like just define this loss and sort of make it work. So what they do is they consider the feature maps after the sixth block of style GAN. And I had pointed out the architecture, but you can simply assume that there are different layers inside the style GAN that it sort of goes through. And we can take a look at this if it's not familiar to everyone. But they sort of look at the sixth layer. I wanted to write n, and I don't know what this has become, but just understand that this is an n. Yeah, there you go. And we look at the sixth layer. So we look at the feature maps of the sixth layer or the sixth block of StyleGAN V2. And we resize F to have the same resolution as the final image. This resizing is done by CV2.interpolate, and they've mentioned that. But if you ever like taken a look at the different functions that CV2 supports, this is one of them. They've been kind enough to just like point that out. You can use different techniques. I'm not sure if there's like a good reason for this, but this is the definition of their loss function. So let's try to understand this. So pi is the initial point that we are working with, and let me not mess up the image. Oops, sorry, I didn't mean to do that. Yeah, so pi is the point that we're initially working with, and we're trying to move it to t, which is the final point. So our goal is to move pi to target point ti, and you could have multiple such points. So that's why the I notation exists. So you're moving point p to t, And what you end up doing is you look at a small patch around P. And then you define a loss function around it. So f of Q looks at the feature maps or the values of the feature maps around these points. So how you're simply calculating this loss function is by making it look at the feature values around each point. Optionally, you could also define an interest area around the image that you're working with. So they also allow for that. And you can see the M value is the optional mask here. But simply put, you have these 2 points, and around that, you have these feature values that you're taking a look at. And you're working with that. So at each motion supervision step, this loss is used to optimize the latent code for one step. So you sort of run or you pass through this in steps. You can just imagine inside the optimizer, you're making these steps, right? So at every step, they say you're trying to optimize towards the final image or you're trying to generate that. As W plus is easier to achieve out of distribution manipulations, they use W plus in this work, which is the final space that you're sort of caring about. So let's just make sure I understand W plus correctly, and I'm just checking that just to be sure. W can be optimized either in W space or in W plus. So I understand W plus is the target state. I might be wrong about it, but that's what I understand. So you're sort of trying to use this loss function to reach towards the final state. Again, the key thing here is when performing back propagation. So of course, this is the loss function and you would back propagate through it. The gradient is not back propagated through the initial point. And this will motivate the model to sort of focus towards the generated image or the final state instead of the initial state. I think this was one of the key factors here, but we sort of exclude this function or this variable when performing backpropagation. So this really makes the model focus towards the final state. Again, to recap, you have the initial points and you have the final points. And then you define or you look at the feature values around it. You normalize them with a certain formula. I'm not getting into the root of it. I'm again simplifying it. But you sort of take a look at the initial feature values and then you look at the final feature values and you have an optional mask that you can define. This is the loss function. The model passes through it. You are trying to learn the generated state or the final target state. And when you backpropagate the loss through this, you sort of ignore the feature values around the initial state. So I believe that really helps the model focus on the final state. Then they talk about point tracking. So let's read through this. The previous step results in this new latent code W dash and new feature maps and a new image. This does not provide the location of the points. So the goal is to update the initial points such that you can get the final points. Sumit is asking a question. So the final target is predefined while training. I believe the data sets sort of allow that. So they've picked up some data sets that sort of permit that, and we'll just take a look at this. But yes, that's my understanding of it. Actually, I'm now that I'm thinking out loud, it's also It should be possible even without having the final target defined, right? Because that's how GANs sort of function. If you go back to the style GAN paper, that's a great question. I'll pin my updated comment on it. I'll go back and check this. I need to double check this real quick. So let me try to do that. But I'm not 100% sure about this. From what I know, it should be possible even without having that defined. Cool. So just looking at my notes, coming back to point tracking, we've been able to generate this new image that we care about, and we have the feature maps around it. And this is thanks to latent code w dash that we've sort of created. Now what you need to do is get the new location of these points. So they say point tracking is typically performed by optical flow estimation or some other approaches. They say these aren't efficient with GANs and they present a new system. The insight here is that the discriminative features of GANs already capture a lot of details, and thus tracking can be efficiently performed via nearest neighbor search in a feature patch. Then they sort of define how they're doing this nearest neighbor search. So in the motion supervision, we had looked at the sixth block of StyleGAN V2, or the feature map of the sixth block, and these are inside the generator. So again, here they mention the feature maps inside the generator. This sort of gives us a new image, and you have the corresponding feature maps, you have the corresponding latent codes, the representation around it. I am just looking at the chart and I'll answer it. This space needs a way of tracking the points across it. So for that, you look at the discriminator now, and their claim is it already captures enough information around the points that you can simply do a nearest neighbor search inside a feature patch. So we already know the feature patch we care about, right, from earlier, and you just do a nearest neighbor search around it. In this way, they say it is updated to track the object, and for more than one handle point, they apply the same process for each point. They are also considering the feature maps after the sixth block of StyleGAN V2. So they are not using neural network for motion tracking because it would make the whole process slower. Um, yes, but they also make the claim that the information captured inside the generator is already good enough that you don't need to like implement anything else. So just by working with what is being captured already, you can sort of go from there. I wasn't I wasn't planning on shutting down the channel. I only shut down the Kaggle series, which I know upset you a lot. Cool. So if there are any questions around this, let me know. But this is sort of the meat of the implementation. Good to see that they implemented it in PyTorch, and they also this is one of the rare times I've seen someone actually cite. I was looking for the word. I've never thought of it. Cite use a citation to the PyTorch paper, and then they give some details around. They use Atom Optimizer to optimize the latent code. They provide the step size for different data sets, and they say we stop the optimization process when all points are no more than a certain pixels away from their target points. And then this is set to 1, so not more than 1 pixel away. They've also created this GUI that we sort of saw on the website. They talk about their experiments and they say it's evaluated using StyleGAN V2, which was pre-trained on FFHQ, uh, a cat dataset, and I'm only familiar with the cat and LSUN car dataset, also the landscapes one. But I've seen this a few times, and I know these are really well known in the GAN community. So if you look at a lot of GAN papers, these would pop up every now and then. So they compare their approach against user controllable LT. And the main criticism of the older one is it does not support a mask input but allows users to define a number of fixed points. They also compare it against Raft and PIP, which are the motion tracking approaches or the point tracking approaches. And they also do this qualitative evaluation. And I believe I'm just reading through this. I'm not sure if they're using human evaluation here. Yeah, I don't think they're using human evaluation here. They're sort of only looking at the generated quality, is what I understand from this paragraph. Cool. So they perform these benchmarks across a lot of points, up to 68 points, and their approach sort of performs the best. And the best thing about it is it just takes a few seconds. So I'm not sure of the image size here, but it's the fastest across most of these approaches, except for user controllable LT, which is surprisingly insanely fast. But you can see the trade-off is in the accuracy across points, right? So their approach performs the best in these benchmarks. And they also compare these on different data sets. They're looking at the MSE laws and the LPIPS laws, which I'm not sure what that calculates. But I just looked at these tables and I was only interested in the generation time. So looks like it is pretty fast and it should be almost real time, at least on a 3090, or if you have a 4090, it should work really well there. Cool. So they mentioned the same things in conclusion, so I'll scroll past it towards one criticism that they have of their own work, which is for out of distribution performance. You can see the example here. For the horse, I don't think a horse would ever have its legs in such a shape. So you can see that the image can get distorted or get sort of disoriented sometimes for out of distribution examples. They've to say good things, they've also managed to make it work with microscopic images, which is really great. I am not an expert, so I can't say if like this is the best interpolation or the change of the image. But everything else, from like at least a human perspective, looks really good. So in the appendix, they take a look at a lot more examples, and you can go through it. Here's another one where the out of distribution pose sort of fails. So if you move the feet to such a distance which is not there in the example, or here's another one where you move the hands away, it sort of the model misbehaves or doesn't give the best example output. But to go back and summarize, I still need to check if the target is already defined. I don't believe it is, but Sumit has asked a great question, so I need to go back to it. But to summarize, the two steps are they take StyleGAN V2 backbone, they look at the generator inside of it and sort of work with the feature maps inside it. So they define this motion supervision, which basically tracks the point across and defines a loss function that sort of forces the model to think of the output image. And then they define point tracking, which sort of looks inside the discriminator and helps you find these points by doing a nearest neighbor search. because they say the discriminator should already be able to capture a lot of details. So these are the two innovations here. Let me switch screen sharing and go back to the presentation. So, like always, I give some suggested homework. Most of the times, people ignore it, so feel free to do that. But I'd invite you to write about the paper on the internet, write a blog post, write a tweet, write a post about it. That, so at least in my experience, really helps me improve my understanding of things once I explain it to everyone. And I've been doing that every single day for the past 2 weeks. So I think that is what forced me to read all these papers that I showed off earlier. So I would invite you to do it. I don't care if you reference the video or not. It's just an invitation for you to share your learnings if you spent an hour watching this video. I have linked my interview with David Lupke, who had worked on a great paper that sort of builds on top of StyleGAN V2 as well. And that shows you how to generate images with GANs that are also trained on a lesser amount of data. And that was also really popular at that time. So if you want, the like things you learn from there, although GANs aren't as relevant, the things you learn from there is how he thinks of research, and that was a really interesting discussion for me. So I invite you to watch that as well. And finally, consider joining the community. It's again the first link under the like button, and subscribe if you haven't already. There are thousands of LLMs. Why should someone care specifically about Palm 2? I I'm not sure if I mentioned you should care about Palm 2. Did I? Where is that coming from? I'm just curious if you have like a reason for it. I have written about the Palm 2 paper, and I can also point those things out real quick. But for anyone else interested, I've sort of ended the discussion around the paper. So you can drop off if you want. I'll just answer any questions that you all have. I found my tweet, so let's take a look at it. The paper is 92 pages. By the way, I had tweeted this out as soon as it came out, and the paper was up on archive yesterday. So I was like ahead of everyone by a week. I'm really proud of that. Anyways, uh, the paper is like about 92 pages, and it doesn't share a lot of details. The things that I cared about were the smallest. So they've released a family of LLMs. The smallest one can run on phones, and it's trained in JAX, which I think this might be the first or one of the only few LLMs to be trained in JAX on TPUs instead of GPUs using PyTorch, I would imagine. And they've sort of really improved their inference cost compared to the older Palm paper, and it's really good at multi languages. So it supports up to 100 languages, which I don't know if it's more than GPT-4, but again, the cool thing was the smallest model can run on your phone, and it's cheaper to inference, which not many people think about, right? So not many people optimize for inference costs. Is looking at implementations for reference bad? No, it's not bad. How else would you do it, right? um I would say this is like a fairly difficult paper to implement. There are also many simpler ones. So the way to do it is look at the paper and look at the implementation of it, and do that enough number of times. Finally pick up a paper that you can work with. But it is challenging, so I don't have a paper recommendation. It's going to be quite hard. Although, again, if you look at some of the LLM papers, so let's take a look at another one I had shared. So this question was by Mohammed. Mohammed, I would invite you to try implementing this paper. It's a very simple paper. It talks about very simple ideas that sort of help you cut down on LLM usage costs. It's like really simple, very like concatenate API calls and your caching queries. I'm suggesting this because once you implement this, it would give you the confidence that hey, I've implemented a paper, I can go from here. So this isn't even like a architectural implementation. It's just how you're making the API calls. I'm sure many people were already doing this, but this paper sort of really defined it. And then you can also take a look at this might be possible for different domains. So I would say you can take a look at Dr. Lama paper. It looks at the medical domain. You can just take a look at any domain at all. So that's another one. Is training on JAX much efficient compared to everything else? I think JAX's main power lies when you're like really scaling up training. So PyTorch originally wasn't, as I understand, designed to work with 10,000 GPUs. JAX always had that uh, ecosystem around it, although it's still early for JAX to be coming around. I had created a series on JAX when it had just come out, and I had done that with this person who's an expert on it. So I would say you should follow Christian if you aren't already. Let me find him real quick. Sorry, I'm just trying to find my mentor's Twitter handle. Yeah, go follow Christian if you aren't already. He's really an expert in the JAX ecosystem and he regularly posts about it. If you ask him any questions, he's also always very kind to answer those. Is there one place where I can learn all about LLMs? Yes, I will be open sourcing it next week. So just follow me on Twitter or LinkedIn or on YouTube, wherever. Or you can just join the Discord, like I said. So I will be creating a roadmap for everyone that you can sort of follow through and read about the papers. I'll also give you summaries about the papers and share my notes. So you can use that. And the other thing I've been working on is creating generative apps. So I shared a few of these earlier, but I'll be open sourcing all of them and you can build on top of them if you want. So this was one that was fairly popular. And this whole app is like less than 100 lines of code. There's a gist as well. If you just check the thread, you can find the gist. But this sort of allows you to chat with any new archive paper. I'm messing up the playback. I did edit this video quite well, but you can check out this tweet if you want. It's called Archive Chat. The idea is I'll open source many such apps that you can play with. Cool. I don't see any more questions, so I will wrap up here. Thanks for watching, everyone. I'm not sure how regularly we'll have these paper live streams, but regardless, I'll keep posting about it. I think I'll do at least one video on LLMs. So thanks for joining. Please stay tuned for that. And I will be open sourcing the roadmap really soon, which I know has been heavily requested. It's coming soon. See you next week.